All right, we are recording. So let me hand things over to group one for them to present their zebrafish SPIM design.
Thank you, Tom. We'll jump right in. Hello, welcome to ZebraStar Optogenetic Systems presentation. We've designed a low-cost, effective, and easy-to-use zebrafish SIM system. As Dr. Trump said, we're Group 1, consisting of engineers Ashley Booth, Alex Lugo, Alexis Hernandez, Natasha Polito, Spencer Schmidt, Michael Seaman, and Gavin St. John. During today's presentation, we're going to cover our hedgehog concept, give a product overview, and then feature some key design highlights before jumping into deeper design analyses and how we address the customer needs. Then we'll finish up with a cost analysis and conclusion. So we'll get right into it. I'll hand it off to Natasha.
So as a group, we felt very passionate about creating a very simple, accessible, and user-friendly design that would be the most biocompatible with the zebrafish. We took a powerful approach to combine our different backgrounds and use our individual strengths like 3D computer-aided design, product lifecycle management, and attention to detail to produce the best design possible. Our economic engine is driven by our desire to maximize profit per customer purchase by focusing on durability and reusability in the design, as well as minimizing our costs to manufacture each subsystem by finding off-the-shelf options and cost-efficient materials. The perfect intersection of our passion, strengths, and economics is to carefully develop a design that is easy to assemble, user-friendly, and long-lasting, which led us to the ZebraStar Optogenetic Systems. Now I'll pass it on to my colleague, Spencer.
The design consists of a 2,256 millimeter laser path to direct the 488 nanometer blue laser to the sample for optogenetic stimulation. The specimen is housed in a custom fabricated imaging chamber. The chamber has dimensions of 76.2 by 76.2 by 38.1 millimeters and is made primarily of 6 millimeter thick cast acrylic panels for visibility and durability. One of the panels also features a 16 by 42 millimeter thin glass window for laser accessibility. The sample holder is also made of cast acrylic to allow for visibility of the sample from all directions and to allow for imaging or stimulation of the sample from below. The chamber also features a roughly 61 millimeter in diameter aerator, which will help to maintain a safe environment for the zebrafish by ensuring that the water in the tank is sufficiently oxygenated. Now on to Gavin for design highlights.
Yeah, so the first design highlight we'd like to feature is our laser window. By using an off-the-shelf microscope slide cover slip, we designed a 0.17 millimeter thick laser window. And by minimizing the thickness of the window, we can reduce laser aberration and deflection to negligible amounts. Using an off-the-shelf cover slip also provides an extremely cost-effective solution and minimizes machining time of the window during manufacturing. During assembly, the cover slip is laid in a machined recessed seat in the wall of the imaging chamber. This eases alignment of the cover slip while the cover slip is being adhered to the wall of the imaging chamber during assembly. And this recessed seat combined with the assembly plan provide a repeatable adhesion procedure to ensure a consistency with the imaging chamber wall. Moving on to the sample holder.
Our sample holder subsystem design, we wanted to focus on an easy to manufacture design in order to minimize the cost. We chose a compound design made of 4 acrylic pieces, bandsawed from the same sheet as the imaging chamber. We chose acrylic due to its high optical transparency of up to 92% and because of its machinability to mount to the LT1 translator. To join the acrylic pieces together, we chose side grip 4 acrylic cement. This is a thin cement that allows for capillary action between the small planes where the acrylic sheets meet. The cement requires smooth edges for a strong weld, so we will mill the edges that meet for a smooth finish. To mount the sample holder subsystem assembly to the LT1 translator, we drilled quarter 20 close fit clearance holes into the base of the sample holder. We suggest for mounting toward the LT1 translator to use 1/2 inch long quarter 20 socket head screws with an aluminum oxide coating. This coating is corrosion resistant and is necessary due to the wet environment inside the imaging chamber. The socket head also allows for an Allen wrench to be used in place of a screwdriver for the hard to reach locations due to the close proximity of the imaging chamber on the optical table. I'll now pass it to Ashley to highlight the aerator subsystem of our design.
So one of the most unique sections of our design is the use of an aerator as opposed to a full filter or pump. We went with a higher quiet mini aerator, and we chose this because the fish is not going to be in the chamber long enough to designate the use of a full filtration system. So the water will need to be replaced in between uses, as due to UF sanitation policies when working with animals. But we need to make sure the water is oxygenated enough when the fish is in the chamber during testing. So that's what the aerator does, is it provides safe oxygen levels for the fish in between imaging sessions. The aerator is also motorless, so that helps reduce any vibration and noise that would disturb the zebrafish when they're in the chamber. Additionally, the aerator can be turned off during imaging sessions. So that way no bubbles or movement of the water will disrupt any of the lasers or the light sheets that are implemented into the chamber during imaging sessions. Now I'm going to pass it over back to Alex.
To optimize our optogenetic stimulation path, we opted to remove the M5 and M6 mirrors from the customer's original wide field path design. This would reduce both the cost and assembly time of our laser path. This removal did require the precise placement of both the DMD and tube lens, as the imaging objective was already in a preset position in lab, and it restricted the locations that our DMD and tube lens could be set. Both the DMD and imaging objective had to be 300 millimeters from the tube lens in order to be within the focal point for maintaining high resolution. Next is the analyses of our SBIM subsystems.
For the first subsystem, we're looking at the laser window. So one of the main things about a laser window was that it was required for it to be much thinner than the chamber walls. Now, to do this, we chose to opt for a thin glass sheet, which was basically a microscope sample, which basically the reason why we chose it is because glass is optically transparent material, and because one of the things that the chamber will be subjected to is hydrostatic pressure. Now, because glass is a brittle material, it can withstand more of that pressure. Therefore, we can increase the size of the window without having to worry about any sort of deflection. So then what happens is, because we chose that material, we are allowed to expand the window and not have to worry about the optical aberrations. Now, in terms of cost, the prototype cost is $167 with 20 cents, and that has to do with the whole assembly. So basically everything in the design. As for prototyping cost, it is $66.25 per unit for 100 units. Could you go to the next slide, please? Now, the window is 24 millimeters in height and 15 millimeters in width, with a thickness of 1 millimeter. The thickness of the window is, in comparison to the chamber walls, is significant. The chamber walls are 6 millimeters, which does demonstrate that there is a large difference between them. Now, the reason why we chose the size and how we maximize the size of the window was through this cantilever analysis. So we know that the hydrostatic pressure, as the chamber goes, like as the water rises, the pressure goes up as we go down. So basically we chose the lowest section of the laser window as the highest pressure, and we use that pressure as our uniform distributed load, and we model it as simply supported cantilever beam, because it would represent a worst case scenario. Now, the formulas there are just generic simply supported beam equations, which were used to develop a MATLAB code that would automatically give you the shear force, the rotation, the bending moment, and the deflection. These were all used to simulate what would be the worst case scenario. And so for the glass, the modulus of elasticity was 72 gigapascals. And from the section that we chose, which was the lowest section, the moment of inertia was 4.2 times 10 to the negative 9th meters to the 4th power. Then the length was 42 millimeters, and the distributed load from the pressure that was found from the hydrostatic pressure analysis was 10.2 newtons per meter. Now, the main important graph here is the deflection graph. The deflection at its peak is about 1.4 nanometers, which might sound like a lot, but that is in the worst case scenarios. One thing to take note is that these values are in the worst case scenario, meaning realistically speaking, these values should never get to this point and should always keep within the safe threshold.
The next major part of our design is the imaging chamber. And so one of the major customer needs associated with the imaging chamber was the specified dimensions, as Spencer stated earlier. These dimensions were 76.2 millimeters long by 76.2 millimeters wide and 38.1 millimeters high. Our chamber was designed with these specific dimensions in mind, and thus was the bounds for the outer dimensions of our chamber. Additionally, the imaging chamber and the zebrafish holder needed to be optically transparent. So that led us to choose acrylic as our material of choice for both of those sections. We went with acrylic as opposed to glass because glass is more likely to break. And so acrylic is more durable and is also lighter. And that was really important when we were thinking about our design. We wanted it to be long lasting, as we stated earlier. So if you drop it and it breaks, that is not what we want. We want it to be able to handle a little bit of manhandling in the lab. But both of them are constructed out of acrylic, and as stated earlier, that has up to 92% optical transparency, which is what is needed for this customer need. The chamber also needed to be laterally accessible by both the 639 nanometer laser and the 488 nanometer laser. And that is via a much thinner laser window that, as one of my partners just talked about earlier, is the microscope slide. Now, to make sure the acrylic doesn't interfere with this, we machined out a hole in the acrylic of the imaging chamber because the imaging chamber is 6 millimeters thick. So we took out a section of that, which is where the microscope slide is placed to allow for that ultra thin laser window. The chamber is a 5-sided rectangular box that does not include a top, and it has 4 8x32 tapped holes in the corners of the mounting. The 8x32 tapped holes are the reason for the thickness of the acrylic. When going back to the resources we had from Design and Manufacturing Lab, it is recommended that there's at least 5 threads of engagement in order to make sure the screw is secure. So after doing those calculations, that told us we needed at least 4 millimeters for the threads. Then accounting for the tip of the screw that would be placed, we needed an additional 1.2 millimeters. Finally, we also wanted to ensure that the water would not meet the screw threads and where we machine the holes. So there was another section of acrylic that we wanted extra thickness of the acrylic where it would not meet the holes. So another 1.2 millimeters was added. And so that added up to a whole 6 millimeters for thickness of the acrylic to ensure the water would not meet the machined holes. And then instead of using, we looked at possibly using a thinner sheet of acrylic for the rest of the chamber. But when we looked at the cost analysis, it was cheaper to just use the same sheet of acrylic for the entire chamber. So therefore, the entire chamber is 6 millimeters thick. Next slide, please. To ensure the chamber was able to mount to the standard optical table, we had to ensure the holes were spaced 50.8 millimeters apart, which translates to 2 inches. The holes on the standard optical table are 1 inch apart, so this makes sure that the holes line up. Additionally, the system is accessible to all human users because it does not weigh much. Again, we went with acrylic because it is a lighter material than glass. And again, the chamber is very small, so it is easy to be set up and operated by one lab technician with no oversight. The prototype does not exceed $300 and is instead $167.20. And then the production cost at an annual 100 unit run does not exceed $200 and it is instead $66.25. Next slide, please. So we didn't just choose 2 inches on a whim for the distance of our holes. We actually found it through a calculation, which you see here. It is recommended that when holes are put into a material, they are both twice the material thickness from both the edge of the material and from another hole in that material in order to preserve its integrity. When doing this calculation, since the acrylic is 6 millimeters thick, that showed us that our holes needed to be at least 12 millimeters from the edge of the acrylic and from each other. Because the customer need states that the holes need to be in the corners of the chamber, we wanted to put them as close to the edge as safely possible. Putting them 12 millimeters apart, we then calculated what that would put as the maximum distance between holes. Subtracting from the overall length of 76.2 millimeters, it showed us that these holes would then be 52.2 millimeters apart. Converting that to inches to see if it's compatible with the breadboard showed it was just a little bit too far apart and came in at 2.06 inches. We needed it to be at 2 or 1, some multiple whole integer multiple of 1 inch. So we shortened that distance down to 2 inches and then used the same equation from above, but instead solved for the minimum distance from the edge. And that showed us that in order to make sure the holes were 2 inches apart, so they're compatible with the breadboard, the holes needed to be 12.7 millimeters from the edge of the acrylic. Now I'm going to turn it over to Natasha. She's going to explain to you about our biosafety and zebrafish handling systems.
On this slide are the 4 customer needs that relate to the biosafety subsystem and the zebrafish handling. By making your design align with the U.S. sanitation practices for aquaculture facilities and ensuring that the materials we used didn't react with common cleaning agents to prevent the production of algae, we met customer need 13. The acrylic material that we chose for the imaging chamber did not have 3 scholarly articles that find it leaches toxic chemicals into the water, which is the zebrafish environment. Therefore, we met customer need 14 because the material is deemed safe for the zebrafish and it will not cause harm. The off-the-shelf Hyger aerator meets customer need 15 by maintaining an oxygenated environment with a flow rate of 6.657 gallons per hour. And lastly, the lab at UF meets the standards of a biosafety clean room because the finishes and materials are non-porous and do not support microbial growth. Next slide, please. So by taking the volume of the imaging chamber, we were able to determine what the minimum flow rate necessary in the chamber was to maintain a proper oxygen level for the zebrafish. The minimum flow rate must be at least 10 times the volume of the tank per hour. As you can see, the minimum flow rate required to maintain proper oxygenation is 3.51 gallons per hour, and the aerator we chose for our design goes up to a maximum of 6.657 gallons per hour, meeting the minimum. Next slide, please. So here we have a summary of our cantilever analysis we performed on the zebrafish sample holder to determine the shear force, the moment equilibrium, and the deflection based on potential modes of failure. The weight of the zebrafish is represented by M on the left figure and by Q0 on the right figure on length 2 of the beam. We performed the analysis to determine if the acrylic cement was strong enough to fix the acrylic pieces together without failure. Next slide, please. And here we have the results of the beam study. It shows that the sample support would have a maximum deflection of 0.437 millimeters, which is about 0.017 inches. The deflection is minimal and as such, doesn't seem to pose any complications to our design. However, all of the values we used for the calculations were for worst case scenarios. We found the weight of the heaviest zebrafish would cause a load magnitude of approximately 0.0027 newtons. However, the zebrafish's weight will probably not reach those highs as the weight was due to specialized diets. In terms of the acrylic plastic, the values of the modulus of elasticity ranges from 2.5 gigapascals to 3.5 gigapascals. And we use the higher end of that range for the calculations. If we were to compute these graphs with average values, which is the average situation, we would result in even smaller deflection, which again affirms that the sample support would be able to withstand the loads. Now on to Alex.
When considering the design of our optogenetic stimulation path, the first customer requirement that we focused on was the preservation of the resolution of the existing 639 calcium imaging illumination path. We met this need by measuring the illumination path in person in lab, and we represented it on our CAD model with red posts positioned on the optical table. The next customer need was specified that we should only use optical elements that the customer had in stock. Our design managed to avoid using any additional components and only removed 2 of the customer specified mirrors from our parts list. It also required a high resolution light patterns for the stimulation of the zebrafish. We met this by locating the DMD and imaging objective within the focal length of the 2 points. The customer required that the 488 nanometer laser beam to be switchable onto the existing calcium imaging path in order to conduct parallel zebrafish brain voltage imaging. This need was met by placing the M1 mirror onto a magnetic base before the first beam expander in order to to easily manually switch the 48 nanometer, 88 nanometer laser beam between both laser paths. Next slide, please. The customer also required a high resolution light pattern to reach the zebrafish specimen. To do this, we used a DMD that was rated for a 1920 by 1080p resolution that first passed the first beam expander consisting of the L1 and L2 lenses. This expands the beam by a factor of 10, and this is then reflected off the periscope assembly to reach the DMD that is on the elevated breadboard that was already set in lab. The customer also required the alignment of all optical elements that we would add for the optogenetic stimulation path. We used Thorlab's optical posts and universal post holders to meet this requirement. These assemblies allow for the precise positioning and fine vertical adjustments of all optical elements for easy alignment. These fasten to the optical table using quarter 20 screws. The last customer need for the laser path was for the sample to be targeted. To do this, the 488 nanometer beam passes through the complete optogenetic stimulation path, and it reaches the partially submerged imaging objective that is located inside the imaging chamber directly above the sample holder. Next, Michael will cover the cost analysis of our SBIM system.
All right, so here's the cost breakdown for our design. So for the prototype run, the total cost comes out to about $167, while for the production run, the cost comes out to about $66 per unit. So the main difference in the two comes down to the difference in price of the off-the-shelf parts as well as the raw materials. So the off-the-shelf parts include the aerator used in the imaging chamber, as well as the microscope slide cover used in the laser window. For the raw materials, we have the acrylic used in the manufacturing of both the imaging chamber and the sample holder, and the epoxy and the acrylic cement to finish the manufacturing. So the difference in these prices comes down to our ability to buy in bulk for the production run. For our prototype run, we were only able to buy a small sheet of acrylic that really rose the price when we try to buy the smaller amount. So the cost per unit for the production run was significantly lower in both the acrylic, epoxy, acrylic cement, and the microscope slide covers. The manufacturing, energy, and assembly costs for the prototype and production run are identical. This is because the manufacturing was calculated the exact same way through a process-based manufacturing timetable. So I went through every single process that had to be done in the manufacturing, whether it be the milling, the bandsaw cuts, or even it comes down to the machine changes on the mill. And I got the figure of $38. That figure was able to be kept relatively low by our choice of getting acrylic sheets rather than using a block of acrylic. Most of our manufacturing comes down to using the bandsaw to actually separate the pieces of acrylic into the ones that we can then glue together. This choice led to the bandsaw contributing about 65% of the manufacturing cost. The rest comes down to the small volume that needs to be milled for the bolt holes or the laser window. This choice also kept the energy costs down due to the real lack or the small amount of subtractive manufacturing. So that helped keep the energy cost to a very small amount. And the last part is the assembly cost, which mainly consists of fastening the bolts into the laser table and attaching the mirrors. And because that's all there is, the assembly should take about 7.5 minutes, keeping the assembly cost relatively low. All right. So that is the cost breakdown. So to summarize why the ZOS SPIM, like I just said, our design is very easy to assemble. Doesn't take much time, has a small number of screws and parts. Most of the screws are the same size, and it's easy to set up and take down. We have a very low production cost made possible by our decisions in manufacturing and our material selections. Our design is durable and long lasting, also due to the material selections and the design. Our device should be able to be reused over and over again for a very long time. And we have a very small amount of manufacturing. Just using one sheet of acrylic for the manufacturing of the sample holder and the imaging chamber really helps out with time and keeps the cost low. And with that, I want to say thank you guys for attending our presentation. Thank you to our sponsors, and we are open to any questions that you guys might have.
Okay. Thanks for the presentation. Any questions from our panelists?
Hey guys, this is Tom Singer from Northrop Grumman. I like that you included an aerator. That's different than what we've seen before, and so I'm intrigued by it. But I guess I wonder, how necessary is it? If you didn't have an aerator, how long would a zebrafish be? I don't know if the word is expected to survive or allowed to be present in a box that doesn't have some sort of oxygenation. So what is that? What capability is that providing for you?
So we don't have a precise figure for you, but we assumed that if you are trying to image the zebrafish and learn about it based on how it reacts to stimuli, then if it is existing in a consistently decreasingly oxygenated environment and struggling to breathe, then that could affect your data.
Oh yeah,
so it's less a matter of
potential,
whether the zebrafish lives.
Yeah, as a potential purchaser, I guess perhaps, I'd be interested in, what precisely that's adding, right? Because that, I think you were saying you're off-the-shelf parts, which sounds like it's mostly this aerator. Is that true?
Yeah. So from my understanding,
so if the off-the-shelf part is essentially the aerator, that's adding something like 20+% of your overall cost, right? It's like $17 out of a total cost of like 66, right? So you're 25 to 30% or so of your overall cost to add this aerator. I'd want to know kind of what the value proposition is behind that. So you were talking about you want to build your box out of acrylic for the purposes of durability, and I like that you're thinking about that. I'll say that you're doing analysis of like deflection of your microscope slide as a window, and I didn't see anywhere in there a stress analysis. And as a stress guy, I will say thank you for not including a stress analysis, because the loads on this thing are minimal, and there's really no reason to do one. But I guess my concern with the glass microscope slide is that's the point where it's going to break, right? If you drop this, that's going to shatter. I like that you put it on the inside of the box, because that's going to have the effect of protecting it. So I think that's good placement. Is there another option other than using glass there? Could you use another material that is maybe a little more durable?
We considered using a plastic microscope slide cover, but determined that the deflection, because it's a much less stiff material, we would have to have a thicker window, which might produce more optical aberrations than a glass window.
The other reason is because
any way to quantify that?
Not off the bat, but the other reason why we picked the glass over any other plastic material was because of scratches. Specifically, we thought that the main concern here, if there was optical aberrations, it would be from just either scratches or just reusability. Plastics are very known for that, and so those would cause issues with the laser.
That was something we found during research too, is while the acrylic is great for the base part of the chamber, it does have more, if it were to be used for a microscope slide, it has more tendencies to be a little bit more finicky with the optical transparency. Nothing that would affect the visual aspect for a person, but for the laser, we wanted to ensure it was as optically transparent and clear as possible. So yes, it could be possible to use a different material, but it wouldn't maximize the use of your laser as well, from what we found.
Okay. It looked like you were mounting your tank to your optical table with screws passing through the bottom of the tank. Is that correct?
That's correct.
Is there any method for sealing the water so it doesn't leak out through those holes?
Yes, sir. So there's actually a 1.2 millimeter layer of acrylic in between the hole and then the bottom of the chamber. So the holes don't go all the way through the acrylic.
So how is this actually going to be mounted to the table?
We're using Thor Labs optical posts and then the universal post holders that they already have in lab. They have a threaded section at the very top.
Those thread into the holes on the bottom. So those are effectively not through holes if you're sealing with another piece. And then what are those, just studs that like slip into the holes in the optical table?
They would be, you'd use a 1/4-20 screw and the optical post would be in the universal post holder. And then you would use a 1/4-20 screw to mount the post holder to the optical table.
All right, so when you're physically putting this in, it's got those screws as studs effectively underneath, and those slip into some sort of receiver that's mounted to the table then?
Yeah, that's correct.
Okay. What sort of tolerance do you have on that?
For the holes in the imaging chamber or for the optical posts?
Well, for the overall system, right? If your holes are slightly out of position, right, or they're slightly angled, your posts have to fit into these receivers, and I guess the overall tolerance of how tightly do you have to control the position and the orientation of those studs to be able to successfully fit it into the receivers on the table?
For the table, it has the universal post holder has a slot that allows you to, it's basically I guess a U shape, and then in the middle would be the 1/4-20 screw. So it allow you to slide it along anywhere where there is a hole in the optical table for placement. So they're
okay. So it's not like a tight fit hole that is intended to hold just like a single post in place accurately. It's something that has some adjustability to it.
Yeah, has a lot of adjustability. It could be vertical and then horizontal for any if in case the holes are not exactly lined up to like an inch apart or 2 inches apart as we had.
All right. And then let's see. I'll skip down my list. On your cost slide.
Yep.
You were showing a reduction in cost of the off-the-shelf parts that was from like $70 per unit to I think like $16 per unit. What's driving it? If the off-the-shelf part is essentially the aerator, do you expect to buy 100 aerators and get like a 80% discount?
Yeah, so we also included the slide covers, or the microscope slide covers, and as the as off the shelf parts, and that's really where you see that cost reduction, because before we'd have to buy the large box of those slide covers, and it'd be around 50 for the whole box, and then once we can use one unit
does
per
that $70 cost, and is essentially you bought a box of 50 slides and are only using one of them?
Yeah.
Okay.
There's also a reduction because you can buy the acrylic cement and epoxy in bulk, as opposed to needing a tube, which you don't use the entire amount of.
Okay, and then I guess the final thing I'll ask is your overall cost is being driven, at least the production cost is being driven by manufacturing. I think that was more than 50% of your overall cost. And you mentioned that you were assuming that it's going to be built for production the same as you're building like a one-off prototype. Are there any ways for you to go in and reduce that, optimize your design for production in some way?
So one of the ways that we thought about doing that is we were considering water jetting, but the way that we saw it for the production, it was we figured it might be better if we just bandsaw it for the first unit, and then that's also the best way we could find a quote. So it's once we were still able to keep the costs low, we decided to go with that, and we kept looking, and it seemed like the water jetting was a comparable amount.
All right, thank you.
Yep, thank you.
Okay, we have a couple more minutes. So if there are any other questions from our panelists?
I have one or two questions, if you don't mind.
You're up.
Can you actually go to the cost slide, please? Because do we have a cost slide?
Yeah, it's two back. Gavin, yep.
Okay.
Right there.
So I will admit Mr. Singer took a lot of my thunder on most of this stuff. Good job. But
Sorry, I didn't realize you were here.
I had meetings for the earlier ones, but I'm here now. So you're the lucky group that gets the first one of me. Congratulations.
Right.
So yeah, I'm in agreement. I'm very concerned when the customer says you have $300 to do this and you come in at almost half of that, because then my first question becomes, now granted, recognize I'm not coming in with any engineering background at all, okay? I barely know a hammer from a screwdriver, okay? So it's literally that bad. So, my first question is, okay, did everything actually get met? Because how did the customer overestimate their own costs so significantly? So I'm not saying y'all are right or wrong on that, but that's just kind of the first thing that triggered me, and it probably would require me to do more research. So go ahead.
Yeah,
I was
so
gonna
go ahead.
You're good, Michael.
Oh.
You're good.
All right, I'll go. So that was also kind of a concern that I had. And I think that one of the main reasons why we're coming in so low is because we're deciding to use these acrylic sheets. Believe me, I was also shocked when I saw how much lower we were, but I checked over it multiple times. I try to do this as many different ways as possible, and it's just with the low cost of the bulk acrylic and the way that we're manufacturing, it's just a lot lower than I or anybody else would probably expect.
Okay. The next thing I would tell you, definitely looking at your manufacturing and your assembly costs, there's no chance that the prototype and mass production is going to be the same. Just for assembly, it's going to take you longer to assemble a prototype because you're going slower. You're trying to make sure everything's right. In assembly, you're going to find out in prototype assembly, you're going to find out something doesn't work, right?
Yeah.
So you're really going to want to consider that. And plus too, when you get into production, you're going to have, more of a streamlined efficiency thing. So that's my first. So then I'm wondering, okay, is the assembly cost that I'm seeing here, is this based on what the prototyping cost? Because it's the same for both ones. So which one's the true number? Is it truly $8 essentially for the one or for the mass production?
So the way that I calculated that number out was through the time estimate tables, and then I multiplied that by the cost per hour for a worker to sit there and assemble this. So I can't really find a way to factor in, knowledge or like previous knowledge of the system or experience into that table specifically. I do agree with you though that it will take a lot less time in the production run. But with the tables and the way that I calculated this, that's what we got for the assembly.
Okay. And another thing to consider too, lots of times when you're assembling the prototype, you yourselves may be assembling the prototype. So you may not have as much assembly costs as you think. you know, obviously if you were to do it mass production, you're going to pay yourselves, because if you're going to work for free doing anything mass production, please come talk to me. I will certainly hire you for something. I will find something. But okay, we will not mess with the tables. Got it, Dr. Trone. But so that is just, it kind of, it definitely kind of looks, it jumps out at me that your assembly and your manufacturing are the same.
Yeah.
I would probably explore other options, just to see. And kind of like you said, going your over-the-counter parts or off the shelf, whatever you call them, dropping that significantly is, I would as an investor, because that's kind of what I come in. I come in with the business. I come in with the, I'm about to give you $5 bajillion. Let me tell you if I'm going to buy this or not. I kind of come in more with that. Okay, let me see the detailed breakdown, because going from 72 to 16, yes, I understand you're going to get some reduction costs when, you know, you're buying 50 slides and you can actually split the cost over 50 units versus 1 unit. But maybe you didn't need to buy 50 slides in the first one, you know, just kind of.
Yeah.
So I would really want to see, I understand in this presentation we can't, but imagine if you're pitching this to get money, like I'm going to want literally 10 slides just of nothing but money, because that's what I want to see. That's where I'm putting my bajillion dollars. And then I agree with the aerator comments. Interesting. Good. I like the outside of the box, but I would also kind of look into that a little bit more. Granted, I am not an engineer, but just my brain of thought goes, I don't know so much if that works. Literally from like, are we recording? Yes. You know, literally from the, you know, Julia has no knowledge brain. So, but that is it. I will step back, but yeah, definitely look into those costs a bit more, because
Absolutely.
there's some things a little funky up in there.
While we're talking about it, Julia, you reminded me something I think I remember hearing was that your assembly cost sounded like you were talking about that's the cost for somebody in the lab to actually install this on the optical table, as opposed to the cost to actually, you know, once your parts are cut to, you know, to glue them together. Is that did I hear that correctly?
Yes.
So you usually, I mean, and certainly like ease of installation for your user is something to consider, but that's not something that you would typically include in the cost here. Your assembly cost is your cost to produce the product that you're giving to your customer usually.
So if you're physically taking the sheets and you're cutting them, you know, you would include that because you're cutting the sheets. But if you're buying the sheets pre-cut, I think, again, not an engineer, work with me here, then yeah, you wouldn't include that, because that comes in your cost of product that you're already buying.
Yeah, so the sheets don't come pre-cut. That's the main bulk of our manufacturing costs is cutting those sheets.
Okay. Okay, so okay. How are you, and I'm sorry if you said this and it didn't stick in my brain, how are you cutting them? Are you doing it in a garage? Does somebody have a place set up? How are you doing that?
Yeah, so there's a bandsaw on the MAE, I want to say MAEB lab that we can use. And
for
that would be the
prototyping.
bandsaw that we use. Yep. So
what about mass production?
It seemed to me that it was supposed to be like a similar cost, at least for factoring and manufacturing, just assume the same thing.
Nope. Nope. Do you think, because believe me, I would love to go to MAE's labs and just use all of their stuff to get my, you know, everything done, you know, just use all of their equipment, use their 3D printers, blah, blah, blah. But prototyping for, you know, this situation, sure, one, you can get done, but once you get into mass production, you got overhead costs. You know, where are you going to produce these? So That's something, you know, to look at too.
Mhm.
And I am done. Congratulations. You survived.
Thank you. Thank you for your questions.
Mm-hmm.
Okay, I actually have a question. So maybe even two. So you've mentioned that you went for the aerator and you're going to replenish the water every time you have to put the fish on.
So with the aerator, not every time the fish has to go on, but every time you switch the fish, like if you choose a different fish, because that's per the UF sanitation policy, is that you need to change the water when the specimen is changed. So that just aligns with those policies. And so that was why there wasn't designated a need for the filter, is by the time the fish may be replaced or like a new specimen comes in, is that you're switching out that water, because again, it is a small tank.
Okay, so my question then is, have you looked into the other parameters that their zebrafish need to have to actually be okay in the water? And I'm talking specifically about hardness, since Florida tap water and other places in the US actually exceed that parameter by about 6 times. And their continuous exposure to that can actually kill the fish, which is pretty sure against their customer needs. So have you thought about that? Have you tried to address that?
I think for that, we assumed he was going to use just distilled water when he was filling up the imaging chamber. And since it's such a small volume, you could probably buy a huge gallon jug of it and make it last for at least a couple of cycles.
Okay. Do you know how much of that is going to contribute to your cost for, since you're refilling it and you have to probably keep a stock of it?
We were just assuming he had water in lab, since he has to have the zebrafish somewhere when he brings them in. I assume he already brought them in water. Or filled
Right, but if
some
you
way to
have
fill
to
it.
refill it, you can't use that water, right?
Well, the aerator was mostly for between testing cycles, since he's stimulating the zebrafish optically and trying to get it to effectively react to the wave patterns. We wanted to make sure the water is oxygenated, since he's having probably more activity than he's used to, especially because it's a larval zebrafish. So it's not exactly the strongest or fully developed.
Okay, well, the oxygen is fine. I was asking more about the nitrates, the chloride, the stuff, and you said that you will be using their distilled water. But then I asked the question about how you keep in stock of that, and if you're making sure, because filtering removes all of those concerns, not their oxygenation.
Right.
I don't think.
Right.
Go ahead.
So I think the assumption was that because handling like the management of the zebrafish test specimens when they're not in testing, that the supplies on hand to keep the fish in water wouldn't be part of our scope.
Okay, but when it is in there,
Like
you would.
water is inserted, then it would become our responsibility to maintain it. But
Okay.
if that's not the case, then we'll for the final report.
Right. Yeah. So as far as I'm aware, that you might want to consider that a little bit more in detail, because that might be against the IRB for their actual research. So you will be probably liable to killing the fish if that does happen. But I did have a second question. When you're producing and you're already running the production run and you're manufacturing for the market, have you researched the shipping of acrylic to remove, like to actually distribute it to your customers?
No, we weren't aware. We didn't think that the like the distribution cost of the product was within our scope once we had assembled and manufactured it.
Right. Well, in my mind, if you signed a contract with someone to deliver a product and then during shipping that product breaks, which actually happens with acrylic quite often, you will need to replace that product but with your own budget. So that might actually increase the amount of money you need to keep for that manufacturer. And then correct me if I'm wrong, Julia. But,
Nope, you're absolutely correct. Because yeah, when you think about it, when you buy a product from Amazon and it breaks on its transport, do you just go, oh shucks? No, you go to Amazon, you tell them to replace it. So transportation is absolutely a cost that you need to, shipping, packaging, transportation, possibly assembly when it gets there, or do you ship fully assembled? How do you just kind of those kind of things too, you definitely need to look at.
Other than those 2 points that I thought about, great presentation. Thank you.
Cool. Any other questions?
Can you kind of walk us through, and I know you're the last group of the day, and maybe, I'm asking the question because we don't have anybody coming after you. Can you kind of walk us through exactly how a researcher would be using your product from the point of installing it, filling it with water, putting a zebrafish in, like what does that actually look like? Because none of the groups have really presented that, all the way through to like, how are they actually taking a measurement, and how are they putting a zebrafish back into wherever zebrafish live?
Yeah, so we can totally walk you through that. I think we have a good slide for the product overview. So if Gavin wants to go to that slide, I think that shows kind of the entire table setup. All right, so I know Alex is very well versed with the laser path, so he can probably explain better on how it gets to the fish. But once this table is set up, from my understanding, and anyone from the group, feel free to jump in if you have something to add. But these laser elements that you see here that are designated laser path are going to be set up previously to the fish coming in. And the hope is that those optical elements aren't moved. So once they're set, they're measured, and they're set for the specimens coming in. And then you see the imaging chamber that is a close-up view is provided in the right-hand view. And so that is going to be set up as well. Alex, can you talk more on like the sample holder and how that gets in there with the zebrafish attached?
Yeah, so you can't see it in this angle, but on the back side of the sample holder, there's 3 holes to mount to the LT1 translator. And basically on the very bottom arm of the sample holder, you'd put, I think it's called aggregose gel, and that would hold up the zebrafish specimen. And then you could easily screw in
So
using
is
this.
the fish like essentially glued to your arm?
Yeah, it'd be glued to the very base of the arm on top.
Okay. And then the laser is shining down from above. Is that what I'm saying?
Yeah, correct. It would go through starts on the left side is where the laser and heat sink setup, goes through that first beam expander, hits the periscope, hits the DMD where it says like the laser path arrow, and then goes through another beam expander, it's called a dichroic that will have a camera behind it to capture the images. And then all that gets reflected down using that right angle mount by another mirror into the imaging objective. That'll be submerged in the imaging chamber. And then the zebrafish will be right there for the on top of the sample holder.
Okay. And so I guess your glue stick is held to something that translates in 2 dimensions, so that you can line up the zebrafish larvae with the beam coming in?
Yeah, it can move. I guess in this view it'd be right to left using that. It's kind of like a turn knob on it's called the LT1 translator. It moves about only like 2 millimeters though. But in this scale, it's kind of significant because it's pretty small units.
Okay. And does that also move up and down?
It doesn't, but you can replace the screws of the LT1 or of the sample holder on the LT1, or you could move the vertical posts that are holding the imaging chamber up and down pretty easily. They have little knobs for holding the posts in place in case it's not lined up.
Well, moving the chamber is not going to help you move the zebrafish because it's not attached to the fish, right?
Yeah.
do you need any sort of vertical actuation ability to, get a fish in the proper spot, or is it just sort of assumed that that is not a critical location?
I heard from the customer that basically the imaging objective is just needs to be submerged and above the zebrafish. Didn't say an exact distance, but I think as long as you got your imaging chamber at the correct vertical height, because he already currently has it set up for the light sheet window. As long as you get that one set up before you set up the sample holder, it should be okay.
So how do you actually get the tank in here? Do you have to like remove the arm before you can put the tank in and take the tank out?
Yeah, you'd have to do the sample holder probably last, and then that imaging objective and right angle mirror mount, that could be easily as just screws that you could easily dismount that and mount it back in place if you needed to get the imaging chamber in, and then mount it back on top, then sample holder.
Okay. And then so they put the tank there, fill it up with water. They mount the arm with a zebrafish glued to it to the little translation mechanism. And then they shoot a laser at it, which is coming in from above. And what are they actually looking at the laser with? Is that through the window?
It would have a camera behind. I guess you see on the laser path there on the top of that elevated breadboard. It makes basically a right-hand turn to hit that imaging objective mount. He didn't give us the specific camera model, but there would be a camera in line with the dichroic that reflects after the beam expander, and it would follow it basically into the imaging objective to capture the image. So it would follow the same path.
Okay, I'm not 100% sure I'm following you, right? So do I have the ability to like get a little like pointer? I don't know if I have any ability to do that.
I'm not seeing any option to give you permission or anything.
Yeah, it doesn't look like I do. But anyway, so I'll try to describe it. So the beam's coming in kind of from the top left-hand corner of that zoomed in image, right? And it's making a 90-degree turn, coming down, and the tip of that whatever sort of cylindrical looking thing is submerged in the water, right?
Yeah, correct.
And the beam's coming out of the tip of that and hitting a zebrafish larvae.
Yes.
And then I guess what I'm not clear on then is where does that beam bounce off of? Does it like go straight back up and return to some sort of imaging device, or does it come out the window at the front? Like,
I think
what are we looking for, and where physically are we seeing it?
Basically there would be a camera that would follow that exact same path, and it would capture. The laser would be projecting basically a wave-like pattern on the bottom of the optical table that would be stimulating the zebrafish, and then the camera would follow the same path into the mirror, would be focused basically onto the mirror through the imaging objective, and would capture from above what it's seeing. So it'd see the zebrafish in the wave pattern below and would capture that image. And then the light sheet would be used at the same time to activate the brain through calcium imaging and illuminating it. So the camera follows the same path as our optogenetic stimulation path, basically captures the results of all that.
I think maybe I need a light sheet to activate my brain here. I'm not following.
I can try if you'd like.
Yeah, but I guess what I'm not understanding is we've got this carefully selected glass microscope slide to allow a laser to shoot through and not be attenuated or whatever, and I'm not seeing how that is in the path of anything that's going on optically here.
So essentially the laser that comes from above is to stimulate the brain of the zebrafish and to like cause neurons to fire. And then there's another, it's not in this image, but the customer has a pre-existing second laser path that comes along that the laser from above came down, the light goes up to the camera.
Oh, okay. I think that's what I was missing. All right. Thank you, guys. And then, okay, so once they've taken the measurement, then what, we sort of swing the little optical piece out of the way here and take the zebrafish off, you know, the little stick the zebrafish is on, we take that off and what, scrape the zebrafish back into its, you know, normal home.
The customer didn't specify what he does after, but yeah, that sounds basically right. If you wanted to change the
So
sample.
you're giving them back like a zebrafish that's glued to a stick, and the customer supplied the glue, the customer supplied the fish, and whatever they do with that is up to them.
Yeah, essentially.
Okay.
Yeah, they
Okay.
specified that they wanted that like to use that kind of glue to mount the zebrafish. So we imagined that they would know how to get it off.
Okay. Is there any concern with if they're going to do any sort of scraping operation to get the fish off? Is there any sort of concern with you know, that abrading the surface of your transparent stick?
So the actual stuff that holds the zebrafish is more like a jello, I suppose, than a glue. So it shouldn't be
Okay.
too difficult to get off.
So you'd scrape that off with like just a plastic
Yeah.
spatula kind of, okay.
Yeah, you can use something pretty soft to get it off.
Okay. All right, thank you guys. I vastly better understand what's been going on. So this has helped me for the previous groups and groups to come tomorrow. I appreciate it.
No problem.
Thank you. Awesome questions.
Okay, we're a bit over time, but like Tom said, we're not in an enormous rush because there's nobody after us, although I imagine you guys have got other things scheduled in your day. So are there any final questions from our panelists before we wrap up? Nope. Okay, I think we're good to go then. So I want to thank you guys one more time for sharing your design with us and giving us a presentation this afternoon. And thanks for sticking around with us a couple minutes past the official end time to answer those detailed questions and get everybody sorted out. Really appreciate all the hard work you guys have put in this semester, and I love how your design came out. So thank you very much.
Yep. Thank you all for coming.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks, guys. Go get it.
Thanks, guys.
Great. Okay. We will leave you guys the room then. Thanks.